Greetings! Today, or at least in this video, we will try to analyze the first fit algorithm. So it's just the analysis of, say, first fit. We chose an online deterministic bin packing algorithm. Now, we bound, or at least we are again try to compute the asymptotic competitive ratio using the wave function method. So this is kind of similar to the analysis of the harmonic algorithm, and we won't do it completely, so it will be only a partial proof, because that's a quite long case analysis, at least one of the directions. Our weight function now is, so remember, to each object there is an assigned size, and we are packing objects of a given size into bins, and into a bin at most one total size can be packed. But we are introducing here an artificial thing, which we called the weight of the object. Wi denoted the weight, the associated weight of the ith object. And basically, I think it's easier to understand if I'm doing this the following way. So it's 6/5 AI was the size of the ith item, plus something which depends on AI itself. So it will be 0.4 if it's a large item, so if 1/2 is strictly less than the AI. So for example, if the size of the object is, say, 1, then we have 6/5 plus 0.4, which is 1.6 total weight for that object. Now this additional cost, which we call the penalty of an object, is quite smaller if this is a smaller object, AI, but at most 1/2. So far it's quite similar to the harmonic, but right now in the third row it will be a bit different. So it's 3/5 AI. It's actually dependent on the size in this case, minus 0.1 if, now it's again an interval, but it's not exactly following the harmonics line, but of course this is not the harmonic algorithm, so it's about first fit, and otherwise it's just 0. So if this is a small object, then we don't give any penalty to the object. So basically I will call this part the base cost, or the base weight, and this part will be the so-called penalty, weight penalty of the object. Now, since we are using the weight function method, again we have to prove an upper bound for the maximum possible weight which we can pack into a single bin, and second, we should prove that the first fit algorithm packs at least some constant amount, some constant weight into each bin, but maybe a constant number. So the two statements are the following. So we can show that into a single bin the total weight that can be packed is at most 1.7. Okay, so that will be one statement, one direction, and the other direction states something about the first fit, namely the first fit, the first fit packs at least one total weight into each bin except at most 2. So again, this is the statement which the algorithm does. It packs a large weight into almost all the bins, but a constant number of them. It's quite similar to the harmonic. In the case of the harmonic, we just proved that there are at most, so all the closed bins will contain at least a weight of 1. Actually, they will, most of them contains exactly a weight of 1. And we also proved that into a single bin you cannot pack more than 1.69 something weight. So this is kind of similar, and this is a typical application of the weight function method. You are just proving a lower bound and an upper bound, and from these, remember, if you apply the weight function method, it means that the competitive ratio of the first fit is at most 1.7 divided by 1 in the asymptotic sense. So this means that the asymptotic competitive ratio of the first fit algorithm is at most 1.7 divided by 1, which is 1. So it's actually inequality here. So you can give bad enough examples on which the first fit has a cost of 5.7. So that's what you should memorize. Say so that the asymptotic competitive ratio of the first fit algorithm is at most 1.7, right? 1.7. Good. Now this we won't prove. We don't prove it here. So the proof is a quite involved and very technical, long case analysis, and well, it's quite hard, but it doesn't give any more insight on the subject. The important thing is to understand what the weight function method is. But this one I will show. So into a single bin, the total weight that can be packed is at most 1.7. So this is what we actually prove this. Okay, so let's just scroll this. Now the base weight is at most 1.2. It's no matter how many objects you will fit. So the base weight base weight is, well, it's the sum of 6/5, say, AIs, for those AIs which are in the bin, which is of course exactly 6/5 times the sum of the sizes of the objects in the bin. And this thing here is of course at most 1, because there's a size limit, so this is just at most 6/5, which is 1.2, which means that we only have to show that the total penalty is at most 1/2. So that's why it's enough to show that the total penalty is at most, well, with at most 0.5, because 1.2 plus 0.5 is the 1.7, which we just want to prove. Okay, so of course, and if we just want to compute the total penalty, then we don't have to deal with these objects because they all have a penalty of 0. So we don't have to consider these. We don't have to consider these. So there are 3 possible size intervals: one for large objects, one for medium objects, and one for small objects. And we are just doing a case analysis based on the number of such and such objects. So we have cases. The first case is that if we have a large object, large object for which AI is larger than 1/2. Now in this case, the penalty is 0.4. So this means that we have to show that all the other objects have a penalty of at most 0.1. So penalty for this guy is exactly 0.4. And since we want to show that the total penalty is at most 0.5, it means that all the other guys can have only a penalty of 0.1. Now, of course, there can be only one such object in a bin. Only one such object. Since you cannot pack 2 guys having a size more than 1/2 into a single bin of unit size. Now, there are 2 subcases. The first subcase is that if we also have a medium object, an object with weight being between, and the lower bound was 1/3, right? So it's between 1/3 and 1/2. So it's 1/3 and 1/2. Then again, there can be only one such object, since 1/3 plus 1/3 plus 1/2 is already greater than 1. So there can be only one such object. If we also have a large object, of course, there can be only one such object and no more. Which means that its penalty is 0.1. Why? Because here we can see that in this case the penalty for this object is 0.1. Now the total space occupied by this object, it's already at least 1/2 plus 1/3, because that's the lower bound for these two objects, which is 5/6, which means that we can only have very small objects next to these guys, and these very small objects don't get any penalty more, so only these two objects will have penalties, but positive penalties. So the space occupied is at least 5/6, which means that no small objects. And in this case the penalty is exactly 0.1 plus 0.4. That's good. Now that was the first case. Now the second sub-case is that when we have a large object but we don't have a medium object, then, well, we can have one small object. Now the small object was between 1/6 and 1/3. Now let's just compute the penalty for these things. So what's this? So what can this be if we have? So the penalty is then is 3/5 AI minus 0.1, which is just between, say, if it's only 1/6, of course it's an increasing function. Now it's between 3/5 times 1/6 minus 1/10, and this is just well, it's 0. Okay, and the other endpoint is when we have the 1/3. So this is just 3/5 times 1/3 minus 1/10, in which case this is 1/5 minus 1/10, this is just 0.1. Now this means that these objects have a penalty between 0 and 0.1, so there's not that much actually. Now if we do have one such item, one small object, then its penalty is between 0 and 0.1. And if we have one large object, no medium object, and one small object, then the total penalty is at most 0.4 coming from the large object, plus 0.1, which is the upper bound of this interval, and that's only 0.5. Yeah. Now we can have two of these objects, so that's also an option. That's also an option. Okay. There will be a second advertisement, so this is just at most 0.5, but we can have two small objects. Oops. Two small objects. It's again between 1/6 and 1/3. Now then the total penalty is, okay, so the penalty was 3/5, say AI. Okay, let's call these guys A1 and A2 because there are two of them. So it's 3 over 5 A1 plus 3 over 5 A2 minus 0.2, right? Because for the first object you have 3 over 5 A1 minus 0.1, and for the other you have 3 over 5 A2 minus 0.1 again. So it's in total 3 over 5 times A1 plus A2 minus 0.2. Okay, now remember, we have, in this case, we have a large object which is already occupying 1/2 of the container. So this means that this guy here is at most 1/2. It's actually smaller than 1/2, which means that this is 3 over 5 at most, 3 over 5 times 1/2, so that's 3 over 10 minus 0.2 is at most 1 over 10. So again, the total penalty for these objects, yeah, that's it. So it's again at most 0.1, which again makes the sum total penalty is at most 0.4 plus 0.1, which is again 0.5. Okay, now we can't have 3 small objects, so we can't have 3 small objects. Because the lower bound is 1 over 6, and these objects should weigh strictly more than 1 over 6, which means that 3 times 1 over 6 is already 1/2, and there are no more, and there is no nut, and there is smaller than 0.5 space left in the container. Okay, so that was the first large case. The second case is that if we don't have a large object, then we have only small objects and small objects, mediums and small objects. But since each of these is having a size strictly larger than 1 over 6, right? So these guys have a size larger than 1 over 3, and these guys have a size between 1 over 6, strictly larger, and at most 1 over 3. This means that these guys, the mediums and the smalls, have a size more than 1 over 6, which means that we can only have 5 of them. So at most 5 of them. Now for these two categories we have a penalty of 0.1, and we have a penalty somewhere between 0 and 0.1, which means that the penalty for these objects is always at most 0.1. So each having a penalty of at most 0.1. So since we have at most 5 objects having at most 0.1 penalties, then we get that the total penalty is at most 0.5, 5 times 0.1, which means that we just finished our short case analysis, and we actually proved that the total penalty is 0.5 and the total base weight is at most 1.2, so the total weight is always at most 1.6 in every bin. Now, proving that the first fit packs at least a weight of 1 into almost all the bins is a similar case analysis, but there are much more cases, and well, you can see some details in the lecture notes if you wish, but actually proving this is not a part of the online algorithms course curriculum, so you only have to know that the wave function method can be applied to this case as well, similar to the harmonic algorithms analysis. So that's for the analysis of the first fit algorithm, and we will continue by an extension of the bin packing problem in the next video. Till then, bye bye.